Yeah, good morning, everyone. It's really nice to be here. I don't come over to this universe often enough. I wanted to start by saying that I was a Clay Fellow, technically in OIR on the third floor some time ago, but I hung out mostly in the ITC because I like to give theorists a hard time. So, and I'm going to follow in that tradition today by telling you a little bit about my observational results, because I am an optical high-resolution spectroscopist after all. We have these really fun and intriguing new results about the Large Magellanic Cloud that really is pushing the frontier in my field. And this was recently published a couple months ago by Ani Chiti et al. In Nature Astronomy. He was a grad student with me, and he is now a Brinson Fellow in UChicago. So let me introduce you all to what I do. So you might not be thinking about metal poor stars all that often, or certainly not from an individual star perspective. If you take the Milky Way here today, we have lots of stars in it, and what we do is we study their chemical composition to learn about what they're made from. But really what we're doing, because they have preserved the chemical composition of their outer layers for billions of years, what we're doing through our abundance analysis is we're studying the chemical composition of this early gas from which they're formed. So I don't really actually care too much about the stars themselves, sniff, sniff, but more about what happened back then. There are 13 billion years in between, and I have nothing to say about that. But of course, most of you do have something to say about that with simulations. So I'm very pleased to see all these biggest ever new simulations. Here's one that came out of MIT some years ago. I don't need to explain that, but it's a really nice compliment, because again, we can look back in time, and you eventually need my input, but I also need your answer. So we all have to work together here. And we do this with the Magellan telescope. I started to use that while I was here at the CFA, and I continue to use that at Magellan, at MIT, and it's really wonderful scope to do this kind of work. So this is the basic idea of stellar archaeology, that we use individual stars that we find in the Milky Way to look back and explore this early time here. Now, we have a few big questions to deal with here, but let me summarize first what we've done in the last 20 years. We found a lot of metal poor stars. You may have heard about this here and there from me or from other people. We have explored the history of the Milky Way and what it's sort of chemically made up pretty well, especially for the halo. We found extremely metal poor stars in dwarf galaxies, which is something that I actually specifically started when I was here as a postdoc, because it turns out metal poor stars are everywhere, as they should. This is all the old stuff that formed early, so you would expect to find it everywhere. And so we expanded it to all the possible dwarf galaxies that you can think of, certainly the little ones. And together with Volker, who's in the audience, we extended this concept to dwarf galaxy archaeology, so from stellar archaeology to dwarf galaxy archaeology, because we learned that you can use an entire metal poor dwarf galaxy actually to study these early conditions, physically and chemical conditions, not just individual stars. So that was nice and helpful. And we find ourselves at a cusp right now, in the sense that early chemical evolution, which is what we study with metal poor stars, right? How the elements were made for the first time or times. And this entire body of work here has shown, and I've given many talks on that the chemical evolution largely looks the same for the Milky Way and the small dwarf galaxies. There's no fundamental differences. So no matter where I find my metal poor star, they will roughly give me the same answer of what happened previously, what events and objects have enriched this early gas. There seems to be some kind of run-of-the-mill, so to say. But let's ask the question, is chemical evolution really, truly universal? And you can already guess that by asking this question here, I'm going to have to say something about that. So let me just summarize here. When we looked at the Milky Way, the halo stars, and stars in dwarf galaxies, we have only been probing gas, early gas, that came from roughly the same place, namely that big blob that eventually made the Milky Way, right? Some dwarf galaxies formed, the Milky Way formed, all kind of from the same region, and eventually, you know, the satellites, or the dwarf galaxies became the satellites of the Milky Way, but we don't need to worry too much about that. So it all came from the same place. So maybe we should expect that chemical evolution is roughly the same because these early progenitors were one and the same, literally one and the same. So what about if we extend, just on paper, this concept of stellar archaeology to something like extragalactic archaeology by saying, like, what if we had stars in the Milky Way here that were probing a different region of space, of the universe, where things may have been different. Different stars, different objects, different timelines, different everything. Because who knows what happened over there? I don't know. It was a long time ago. So we tried to do this. Let me tell you what happened. This is the summary of what I just already mentioned, right? This extragalactic region, how can we start probing further and further out and extend this concept of stellar archaeology? To answer this question, is chemical evolution actually universal? Because I'm pretty sure, and I know that I've talked with many of you about chemical yields for simulations. You always use one prescription, and that's it. So what if it needs to be different? And in order to test that, we observed stars first in the large Magellanic Cloud. The small one is in the works, so I don't have much to say about that yet. It's much harder. The stars are much fainter. But I'd like to clue you in what we found about the LMC. So first of all, I expect you all know that the LMC, or why is the LMC an interesting target here? The LMC is on its first infall to the Milky Way, so that implies that it formed somewhere else from a different blob of gas than the one that made the Milky Way ultimately and its satellite galaxies. So many of you have even worked on that. I was just talking with Elena, and obviously you all remember Gottina Bessler. She was a student here when I was a postdoc. So the LMC is a very interesting target from that perspective. And so we set out to extend stellar archaeology, just in its principle, to yet another dwarf galaxy that I had not worked on before. I'm slowly making my way up to larger systems. And here is a long story cut short in my little pyramid. If you want to do this kind of work, you have to do these 5 steps. First of all, you have to actually figure out member stars. It's not trivial. You might think like, oh yeah, this star is in the LMC, but no, you have to actually show that first. Then you need a very efficient metallicity selection procedure because it actually, A, you need that information, and B, it actually helps with the member star selection. And I'll talk a little bit more about that. Then you need high-resolution spectroscopy of selected member stars if you want to do stellar archaeology with those. Then you need to determine all these chemical abundances, and then you need to compare your abundances with various other populations or groups of stars. So to cut a long story short, I just want to clue you in on a few highlights. A few years ago, together with Ani, who ultimately wrote this paper, he developed a new technique to measure metallicities from narrowband photometry of whatever is in the field of view. So this is a very powerful new technique where we basically do spectroscopy with photometry. So we actually, let me just skip to the next slide here. This is the interesting part. So this is a stellar spectrum. Here is the wavelengths of the calcium H and K lines, which are blown up here. you can see two stars are shown here with different metallicities. So this is 1/10 of the solar abundance. This is 1,000. We like these stars here. -3 is a magic number because this gets you into the one progenitor regime, right? You only need one supernova to give you a star, a next generation star, and it will have around -3. And you can see that this star here, the spectrum of this star, has a lot less loss in flux. So if you put a very narrow filter over this, your metal poor star will actually blink higher, brighter, because there's less absorption, because it's more metal poor. That gives you a bit of a knot in your head, but I think the idea is hopefully clear. So we work pretty hard to get very precise data, small photometric errors, and then spend many nights at the telescope confirming this technique and also the photometric metallicities. And you can see here just a scatter plot. The scatter around -3 is at the 0.3 Dex level, and at -2 is 0.15, 16. These uncertainties are as good as what you get from medium resolution spectroscopy. But the amount of time it takes with the telescope is a lot more if you take spectroscopy than if you take a few images. So we have at least an 85% recovery rate for stars at -3. When I did my PhD in Australia a long time ago, my success rate was 11% for stars below -2. So this is too good to be true. But it's also almost 20 years in between. So that's what progress looks like. And it has really allowed us to open up this exploration of various other dwarf galaxies. So for those of you who are curious and know a little bit about the color magnitude diagram, so there are lots and lots of fairly reasonably bright targets. 16th magnitude is quite doable with high resolution spectroscopy. All the red ones are candidates. We chose the brightest one up here. We observed 9 or 10 stars with Mike. That's the high resolution spectrograph to do a full chemical abundance analysis. And then we observed another 15 stars later on to just with MAGE, with lower resolution spectroscopy, because we wanted to check on one thing, but I'm not going to tell you right now what that was. That comes in a moment. So let me lead off with one of two cool things. We found one star at a metallicity of -4. In the halo, you don't accidentally find -4 stars. They are way too rare. I have looked for these stars for too long to know that they don't just show up. So here's one. 1 out of 10, kaboom, -4. Now, -4 is in the second generation regime. So we have a star now in the LMC that traces the whatever POP3 stars were, in the gas that made the LMC, which, as I said, because the LMC is on the first info, came from really far away. This is really exciting. For the first time, we're probing extragalactic POP3 stars. That's really cool. Here is the magnesium line, for those of you who are interested. Magnesium over hydrogen here is almost -4, which means it is actually alpha enhanced. Oops, I forgot, that should be iron here. Magnesium over iron is 0.4, so it's an alpha enhanced star. Totally normal -4 star, if you could say that. And it is, I forgot to say that, is the lowest metallicity star in any outside external galaxy, right, except for the Milky Way. So this is a really big step forward for us. Now let's look at the chemical abundances of this friend. We have the alpha enhancement, as I already mentioned. So, here you can see the gray stars are halo stars for comparison. There's some intermediate elements, and there's a good amount of overlap here. So that means that whatever we're probing in this extragalactic environment was, dominated by core collapse supernovae of some kind. So check box for that. Then we have the neutron capture elements. We can only get strontium and barium. And barium, you can see, is even an upper limit. And it creeps here at the bottom end of what the halo star range gives. And you could say, like, well, this could be interesting. But we have seen that kind of behavior in all of the other satellite dwarf galaxies. While this is very interesting, it's not atypical. So all other UFD stars and many of the dwarf spheroidal stars have that as well. At almost those low metallicities, we don't have any -4 stars in those systems, but we have -3, -3.5, give or take. So that means when you have low absolute values, right, that we have no R process in those systems. Okay, so nobody needs to worry about neutron star mergers, at least not early ones with short in-spiral times. Who knows what has happened since then? And perhaps there's a limited R process going, which means that it's basically a failed R process. You make some of the lighter heavy elements like strontium and barium, but it kind of peters out. So it tries, but it fails. That could very well explain why we have a very low barium upper limit. Right? So something must have made that strontium. There are strontium atoms in that star, so they got to come from somewhere, most likely this limited R process, which is associated with core collapse supernovae. Right? Above the protoneutron star, it tries to do some neutron capture, but it just doesn't have enough oomph. So it's pretty consistent picture, gets the check mark. So it was probably some massive first star that tried to do its thing. That's the conclusion here. So yeah, it looks like everywhere else. And if I show you here the abundances, not just of the one -4 star, but of the sample of 10 stars. Again, in gray is the halo stars. In red is the new LMC stars. You can see that there's broad overlap, right? For an astronomer, this is really good agreement. So the evolution of all these elements, this is what we can deduce here, is not fundamentally different in these two systems. Okay, cool. So it looks like it supports chemical evolution as universal. When you have core collapse supernova going, they will always give you the same thing. Cool. That's assuring. That's assuring. But what else could we expect, and what else have I not yet talked about? And that element is carbon, and this is where things get interesting. So carbon is here. You can see it's at the bottom end here of the halo star range, and that is unusual. That is unexpected, certainly for a metallicity of -4. So in the halo, most stars have a very high carbon abundance of at least 1. You can see the scale here goes up to 3, and some even have like 4. And this guy here, this is the -4 star in the LMC, our new friend, has a subsolar carbon, but actually that's a -3. So it's very low. What is going on? What's the story here? So let me just refresh you on what's going on in the Milky Way. This is an old graph, but you can see if you go from -3.5 to 4.5 or so, there are not that many stars for starters, okay, but many have quite large carbon overabundances. Very few have low values, and these are all measurements. Right? So our guy doesn't have that. Interestingly enough, it depends a little bit on what angle you want to take and how you want to interpret your data. But if you take a fresh look at the stars that we looked at in the ultra-faint dwarf galaxies and the classical dwarfs, we haven't really found any of these crazy carbon-rich stars either. But we always argued, well, maybe we just haven't observed enough stars. And if I only have like 3 stars in a dwarf galaxy, it was like, that's a fair argument to make, right? But maybe it also showed us something different, and we just didn't have enough insight to interpret it correctly. So my point is here, maybe what we're starting to see is that in the dwarf galaxies, the prevalence of carbon-rich stars at the lowest iron abundance is not quite as represented as in the Milky Way. And this actually fits into many discussions that I certainly had here and even before with Volker and with Avi. They had this important paper in 2003 on the formation of these most metal-poor stars, most iron-poor stars, I should say, saying that, okay, they have to be carbon-rich because the POP3 stars needed to produce all this carbon and oxygen so that atomic fine structure line cooling from carbon and oxygen would kick in and then actually enable the formation of small stars, right? So ever since, and my career is made on the discovery of carbon-rich iron-poor stars, ever since, the first stars have been strongly associated with producing a lot of carbon. And now we have this result in the LMC where I'm saying, well, the progenitor was not carbon-rich. Now, you can now say, but you're only talking about one star, right? Well, let's look at the other stars, because this is why we got 15 more stars observed just for the carbon. You can use lower resolution spectra. And none of them are carbon-rich. Here's the plot. This is 0.7, right? The other plot went all the way up here pretty much to 3. And here, nothing crosses 0.7. There are some evolutionary effects going on in the star. As they go up the giant branch, the natal carbon abundance goes down, but we can correct for it. If we do, we push them to the limit here, but not above. So where are the carbon-rich stars in the Large Magellanic Cloud? 25 stars is a lot. I talked about having 2 or 3 stars in an ultra-faint dwarf galaxy. That's sort of typical. So here we have, a lot more. They are not there. So what does this mean? That means that the progenitors did not produce a lot of carbon, or they were very much diluted. So we can start debating that. So maybe there weren't faint supernovae that give you a lot of carbon and have low iron. Maybe there were no massive stars with that are fast rotating and have a lot of winds, as has all been proposed to explain the prevalence of carbon-rich stars in the Milky Way. So as a first hint, and the last word hasn't been spoken, is that maybe the carbon production is environment dependent. Maybe it is not universal. And we have other hints from the ultra-faint dwarf galaxies. There are no carbon-rich metal-poor stars in the bulge, as far as I know, certainly not at the lowest metallicity. And a couple years ago, we found a low metallicity, thick disk-like component in the disk. And that one had we rediscovered a handful of very low iron stars that had a tendency not to be carbon-rich. And I was like, what's going on? This is weird. But all of these accreted things now give that kind of picture. The high carbon stars are missing. So this is my summary slide. Galactic archaeology can now be extended to an extragalactic scale. We are going to run out of targets sometime soon, namely after the LMC and SMC are worked. That's it. But nevertheless, at least we have 2 data points, and I learned 1 star or 1 thing is a discovery, 2 is a sample, and 3 is a population. So we will be at least at a sample, right? Maybe with 3, if we get the SMC in there and shows the same picture, we'll be at a population, right? So then that is the proof. But nevertheless, I think it's an important step forward in our exploration of this sort of near-field cosmology approach, where we use local stars to really now go on the extragalactic scales, using this trick of saying, okay, if we can't go over there, LMC come to us, right? I think this is really neat. The question remains, is element production universal? I think we have to go a little bit back to the drawing board and have more discussions about carbon, how we make carbon, and how environment dependent the stars and their carbon production is. The results are too interesting and too varied right now to know, we can no longer sweep it under the rug. At least I'm excited to pull it out from under the rug and revisit it in a new fashion. So we all have work to do, but I think it's not just on the observers. I hope to chat with some of you to hear what you think this could be, and how we can work together to resolve this. Thank you.
Is it working? Yeah. Okay. So thank you very much. Let's get some questions over here.
Thank you very much for a beautiful talk. I got really puzzled. Can you have any idea of how can the environment affect the carbon production rate?
How can the environment?
How can the environment affect the carbon production?
Well, it depends on, this is where the initial mass function comes in. Honestly, I don't really know. This is why I'm saying we have to kind of start from scratch a little bit to figure out what that could be, because I don't have, if anyone has an alternative explanation, I'm totally game, right? But how can have all the small things have no big carbon and the big thing has big carbon?
It was the original suggestion. The original suggestion from metal poor, iron poor, carbon rich stars is that when the explosion takes place, the core makes a black hole, whereas the outer layers that contain carbon go out.
Yes.
And so you don't get the iron, you get the carbon, but
exactly. So that mechanism was cooked up specifically to explain the most iron poor, carbon rich stars. And maybe there's some environmental impact, influence on what determines whether these things, if they ever existed, can show up everywhere. That's my best guess too. I don't know, I'm intrigued.
Thank you for this new challenge for theory. Just a quick technical question. Once you taught me that oxygen is tough, do you have any because of course, right, in Avi's, in my paper, of course, we said, right, we had a combination of C and O, right? That was sort of the idea. So do you know anything about oxygen for those stars?
Nope, and it's not coming. It would be very, very difficult, right? The brightest ones are 16th magnitude, and it just goes worse from there, right? And we're talking magnitudes. Oxygen is in the UV. That was really hard with my 2005 star, and that was 13th magnitude. Unfortunately, that's an absolute no-go. I wish it was different. If someone can donate $1 for a bigger telescope.
Thanks. Nice talk. So my understanding was that much of the local stellar halo now we think came from a few objects like GSE and other kind of small galaxies that are we're not that different in mass from the LMC, SMC. So would you expect those to have, or do we know whether those have the same kind of trends?
You're asking the right question. We haven't looked yet. Again, this is pretty fresh. This work takes quite a bit of time. At least we have the selection technique worked out now. That took a few years, and getting the selections and the data and all of that. Thanks to Gaia, we have a much better way now, to do precision member selection. And together with the metallicities, you can actually select even better, because certainly if you are interested in the low metallicity regime, having metallicity cuts out the entire haystack, basically. We haven't looked at GSE identifications. I think we have talked about this maybe a year ago with my guys, but maybe we need to revisit that now. We're trying to assemble the SMC sample right now, but yeah, one galaxy at the time.
So this may be a naive question. So if the star is absolutely the first generation star which formed out of the primordial thing, so then you should expect it to be completely metal-free, right?
Yes.
Like there should be no other elements beyond lithium.
Yes.
And those stars that you talk about are basically after that.
Second generation.
Second generation.
Correct. So the first stars would have been very massive, at least canonically. And then the ones I'm talking about are long-lived, low-mass stars. I'm sorry, I should have said that. So they are still around today, but they're formed at this early time because they have very long lifetimes, 15, 20 billion years. So those are the ones that we're targeting.
Do you expect any first generation star to have a low mass by any chance?
Thank you for the question. We will have a conference on that in New York in 2 weeks. wouldn't it be nice, right? As Volker said yesterday, we haven't observed any parent stability signature in the metal poor stars. And along the same lines, we haven't found anything that looks super unusual, except for the high carbon-rich stars. That was sort of the pinnacle of the unusualness in metal poor halo stars, which I'm now taking away. But we continue to search. If there is one, I hope eventually it ends up on my target list. I will let you all know when that happens.
All right, let's thank Anna once more.
Okay.